Imagine suddenly all clocks freeze, all motion halts, and the world stands still. In science fiction, this sounds thrilling, but physics tells a very different story. To a physicist, time is not an independent force we can switch off. It's a dimension woven into the fabric of spacetime. As cosmologist Sean Carroll explains, time is just a label on different parts of the universe. It tells us when something is happening. In other words, time coordinates events in the universe, not a separate entity with its own momentum. A deep field theory production where science meets the infinite. This video explores what modern physics, from Einstein's relativity to quantum theory and thermodynamics, really says about stopping time. Einstein taught us that time is relative, intimately linked with space in a four-dimensional space-time. Two clocks in motion can disagree on elapsed time. A fast-moving spaceship's clock runs slower compared to one on Earth. But crucially, each clock still ticks normally in its own reference frame. There is no universal master clock we can pause. In special relativity, the proper time experienced by an object depends on its velocity according to the relationship on the screen. As the speed v approaches the speed of light, c, the square root term approaches 0. In that limit, the proper time between two events also approaches 0. This means a massless particle, like a photon, experiences no passage of time at all. Its clock is effectively stopped because light travels along null paths. But any object with mass can never reach that speed, so no human or particle can experience this timeless state. Even in general relativity, gravity can slow time but never truly pause it. A clock falling toward a black hole's event horizon appears to slow endlessly to an outside observer, yet the falling observer's own watch continues ticking normally. There is no magical perspective from which time halts. Relativity tells us that all frames are equally valid. In fact, Einstein's equations suggest a block universe, a four-dimensional structure where past, present, and future coexist. In this eternalist view, time doesn't flow, it simply is. Asking for time to stop is like asking to cut a slice out of a solid block. It doesn't make sense. Physically, if time somehow froze, motion itself would vanish. Motion means change over time. Carroll puts it clearly. Motion is change with respect to time, so time itself can't move. If time stopped, all motion would stop too. Pendulums would hang motionless, electrons would stand still in their orbitals, and even light rays would freeze mid-flight. Quantum theory treats time differently from other quantities. In quantum mechanics, time is not an operator but a parameter that describes how a system evolves. The Schrödinger equation shows that a system's wave function changes smoothly over time. If we were to pause the time variable, the wave function would stop evolving. The system would be completely frozen. Interestingly, there's a real quantum effect resembling this, the quantum Zeno effect. When a system is measured continuously, it can effectively stop evolving. For instance, an atom being constantly observed can be prevented from decaying. But this is a local phenomenon, not a universal halting of time. In quantum field theory, all fields oscillate and interact through time. If time were globally frozen, every field and interaction would be suspended, creating a perfectly static vacuum. However, the uncertainty principle involving time and energy implies that extremely short time intervals allow large energy fluctuations. If time were reduced to 0, these fluctuations would become infinite, a physically meaningless scenario. At the deepest level, our normal understanding of time may not even apply. At the Planck scale, around 5.4 times 10 to the power of negative 44 seconds, physics as we know it breaks down. Before 1 Planck time after the Big Bang, it's unclear if the concept of time even has meaning. Some theories of quantum gravity, like the Wheeler-DeWitt approach, suggest that time might not exist fundamentally, but instead emerges from more basic physical processes. Yet none of these theories allow for pausing time in any ordinary sense. Our everyday sense of time's passage is deeply tied to entropy, the measure of disorder in a system. According to the second law of thermodynamics, entropy tends to increase, giving time its forward arrow. As Arthur Eddington famously wrote, "When disorder increases, the arrow of time points toward the future. When it decreases, it points toward the past." This arrow exists because the early universe began in a remarkably low entropy state. Since then, entropy has been increasing, driving all change from stars burning to people aging. If time were to stop completely, entropy would stop changing too. The universe would be locked in a perfectly static state. In fact, a global time stop would resemble the heat death of the universe, a condition of maximum entropy, where no more energy flows and no processes occur. Lord Kelvin described this as the cessation of motion and exhaustion of the potential energy of the universe. In other words, if time ceased, everything would become permanently frozen and lifeless. General relativity predicts some extreme environments where time behaves strangely though never truly stops. Near a black hole's event horizon, an external observer sees infalling matter slow to a crawl, its light increasingly redshifted until it fades from view. To the falling observer, however, time continues normally until they reach the singularity, a region where space-time curvature becomes infinite. At that singularity, the equations of general relativity break down. One might poetically say that time ends there, not because it pauses, but because it ceases to be defined. A similar situation occurs with the Big Bang. In the standard cosmological model, time itself begins at the Big Bang. Asking what came before is meaningless, just as asking what lies north of the North Pole. For the first 10 to the power of negative 43 seconds after the bang, the Planck time, our physics cannot describe what happened. In both extremes, black holes and the Big Bang time doesn't stop, it simply loses meaning. Combining all these insights, it becomes clear that stopping time is not physically meaningful. Time is not an external mechanism that can be paused. It is the very framework that allows change to occur. If time halted, all processes would freeze, and even the act of noticing that freeze would be impossible, since perception and thought require time to flow. In a frozen universe, all dynamics cease. Every clock, organism, and particle would stop. Light and signals halt. Photons couldn't travel, leaving complete darkness and silence. No energy exchange occurs. Heat, reactions, or decay processes would all stop. The result would be an eternal, motionless snapshot, a block universe frozen in every detail. But within physics, that snapshot already exists as part of space-time. The question, what happens if time stops, defeats itself, because nothing can happen without time. Even in science fiction, if someone could freeze time for others, they would be utterly isolated, unable to move, breathe, or see, since air, light, and even neurons in their brain would be frozen too. Relativity forbids any single perspective from halting time for all observers. Modern physics makes one thing clear: time cannot be stopped. Relativity, quantum mechanics, and thermodynamics all depend on the continuous passage of time. Freezing time would mean freezing every process, every motion, and every experience, leaving no observer to even notice. Instead of trying to halt time, physicists explore how it bends, stretches, and perhaps emerges from deeper physical laws. In black holes, in the early universe, and at the Planck scale, time may end or begin but never stand still. The time-stop idea ultimately shows us how deeply time is woven into every aspect of reality. If time ever truly ceased, there would be no sound, no motion, no thought, and no one left to witness the silence.